All right, very good morning to all of you. So, welcome on another session of questionnaire series, part 4. And in this session, we'll be discussing some questions which is very important for IIT JAM 2021 examination. Okay, so I hope my voice is audible and the slide is visible. If both things are working fine, so you can comment down in the comment section so that we can quickly start off with our session. Very good morning, Bharti. Good morning, Davdi. Good morning, Atanu. Good morning, Tarunesh. Now let's start off with today's session. So I hope my voice is audible. Great. Okay. Let's take first question. All right. So this is the first question for today's session, and the question is: a system consisting of 2 moles of a gas expands adiabatically and reversibly from a volume of 500 liters, and basically temperature is 373.15 kelvins. Okay, to a volume of 20 liters. Okay, so this is your initial value, this is your final value, and you have to find the final temperature. Very good morning, Rajendra. So this is the first question. I'm giving you 1 more minute for this question. You have to tell the final temperature and initial value, final value of volumes have been given and temperature is given. Good morning, Ashoka. Good morning, Rustika. So yes, what is your answer for this question? It's basically direct formula based questions, okay? Gamma value you have to calculate, okay? Just see the equation, you can calculate gamma value. Alright, so let's solve this question. Let's see what is given in this question. A system consisting of 2 mole of an ideal gas, okay? So N is equals to 2, number of moles have been given to us, okay? Expands adiabatically. So the process is adiabatic, right? Plus reversible. Process is adiabatic plus reversible, and basically it's nothing but your expansion. Right, so from a volume of 500 liters, V1 is basically 500 liters and V2 is 20 liters, right? Then the temperature is given. Temperature is 373.15 kelvins, okay? So these all values have been given to us. Now what we have to find out? We have to find out final temperature, okay? So the process is adiabatic and expansion. So we can use, we have temperature and we have volume, okay? So we have to find final temperature. So we can use this equation, T1 V1 gamma minus 1 is equals to T2 V2 gamma minus 1, okay? Can I use this equation, T1 V1 gamma minus 1 is equals to T2 V2 gamma minus 1? So this is your equation, okay? This is basically your equation, okay? So now what we have to find out, right? Yeah, so this is not 500 liters, this is 5 liters, okay? Right, is it clear, Atanu? This is 5 liters, not 500 liters, okay? So now this is your expansion, 5 liters to 20 liters, okay? So T1 is given, we have to find out the T2 temperature. Now what is T2? What is the value of T1? T1 is 373.15 kelvins, okay? This is your T1, and V1 is also given to us, that is 5 liters, okay? Gamma minus 1 is equals to T2. T2 we have to find out, and V2 is also given, that is 20, okay? Gamma minus 1. So we have to find out this T2 value, okay? So now 373.15, 5 divided by 20 gamma minus 1 is equals to T2. So this is how I can find out the value of T2, okay? Now what we need gamma. What is your gamma? Gamma is nothing but Cp by Cv, okay? This is your gamma. And the question is a system consisting of 2 mole of a ideal, basically a gas, okay? So what we can take? We can basically take your monoatomic gas, okay? We can take your monoatomic gas if it's not mentioned in the question. So for monoatomic gas, what is the value of Cv? Yes, everyone, for monatomic gas, what is the value of Cv? Value of Cv is basically 3 for translational and 2 for rotational, okay? So 3 by 2 R. 3 by 2 R, okay? So if Cv is 3 by 2 R, so Cp would be 3 by 2 R plus R, that is 5 by 2 R, okay? Cp would be 5 by 2 R. Now we have to calculate gamma. So 5 by 2 R divided by 3 by 2 R, this value would be 5 by 3, okay? This value would be 5 by 3. So gamma is equals to 5 by 3. So gamma minus 1 would be basically, it would be 2 by 3, okay? This value would be 2 by 3. Now you can substitute the values. We have 373.15, right? Then we have 5 divided by 20, and we have 5 by 3, 5 by 3 minus 1, that is 2 by 3, okay? So what is the value of temperature you are getting? What value of temperature you are getting after solution? This is the expression, 373.15 into 5 by 20 raised to the power 2 by 3. This is how you can find out your final temperature. Now just calculate it and tell the correct value. Great, okay. So the correct answer for this question would be 149 kelvins, okay. Correct answer would be 149 kelvins, okay. See, the decimal places, okay, basically should be correct if you have to report the correct answer in decimal places, okay. So approximately the value would come 159 kelvins. So this is how we can solve this question, okay. And see, we can prove one more thing if our concepts are clear, that this is your adiabatic process, and in adiabatic process always temperature falls down. Okay, so this is your starting temperature, 373.15. Now this is your final temperature, so always it goes down. Okay, so T2 is less than T1 in case of adiabatic process. Okay, I hope this question is clear to all of you. Any doubts in this question? Is it clear? Right, I hope it's clear. Now let's go to the next one. So the question is the correct order of the soft character as per HSAB principle of the central metal ion is. You have to find the correct order of a soft character as per your hard soft acid base rule. V1 T1 V1 divided by T1 is equals to V2 by T2. Why we cannot use this statement? Because this is valid for basically your this is not for your adiabatic case. Okay, this is not for your adiabatic case. In case of adiabatic and reversible change, we have to use gamma. Okay, we have to use gamma. Central metal is your chromium. Okay, we have four complexes of chromium. So this is 2 minus, this is a minus, and this would be 2 minus. One second, okay, just let me read this question if in case it's not visible. So metal is basically chromium in all four complexes, and in first complex we have CrO4 2 negative. Okay, chromium with 4 oxygen ligands 2 negative. This is our first complex. Then we have CrCl4 negative. Okay, CrCl4 negative. This is your second complex. Then we have chromium with bipyridine ligand. Then we have chromium with carbonyl ligand. Okay, so we have four complexes with oxygen, chlorine, bipyridine, and your carbonyl ligand. Okay, so this is your four complexes. Alright, so let's solve this question. What we have to find out? We have to find out the correct order for soft nature. Okay, this is the question. So let's do one thing. Let's calculate the oxidation state of chromium in all these complexes. Okay, so oxidation state of chromium in first complex is +6. Okay, it's basically +6. Over here the oxidation state is +3. Alright, over here the oxidation state is 0, and on this complex the oxidation state is your -2. So this is your oxidation state for in this four complexes. Okay, this is your oxidation state in four complexes. Okay, now let's do this question. So chromium is basically present in +6, +3, 0 and -2. Okay, so we know that if your oxidation state is increasing, so hardness would increase or softness. If oxidation state is increasing, so it's directly proportional to hardness or softness. Yes, everyone, if your oxidation state is increasing, it is directly proportional to hardness, right? That means the hard character of the complex is basically increasing. Okay, so this is the concept over here. So in this first complex, the oxidation state is +6. Over here it's +3. Over here it's 0 and -2. Okay, so if basically your oxidation state is increasing of your cation, if your oxidation state is increasing of cation, so what we can actually say that polarizing power, okay, polarizing power of this cation is increasing, right? Polarizing power of this cation is increasing, so hardness is basically increasing. Okay, so correct order is basically option A, right? Because we have to write down the order for soft character, and this is the most hardest compound over here. We have first, then second, 0 and -2. Over here the oxidation state is -2, so this will have maximum soft character. Okay, I hope it's clear to all of you. Any doubts? That option A is going to be your correct answer. Clear, everyone? Any doubts? Is it clear? So correct answer is option A, and it's based on your oxidation state. Alright then, so let's take next question. So this is your next question. For air at 300 Kelvin and 25 atms, your Joule Thomson coefficient is given, that is 0.173. This is 3, okay? 0.173 Kelvin atm inverse. So Joule Thomson coefficient is given. So if a Joule Thomson expansion is carried out from a pressure of 1 atm, the value of final temperature if the initial temperature is equals to 300 kelvins. Okay, so this is your question. Yes, okay, so both things are basically correlated. Okay, your radii concept, okay, and your size concept basically. Okay, both things are interrelated. So we know chromium is in +6, chromium is +3, chromium is in 0 and chromium is -2. Okay, so as we are increasing electron density, the radii or the size of the metal will definitely increase. Okay, so this metal will be now soft in nature. So this could be your explanation, or you can go with your basically Fajan's rule also, polarizing power. Okay, so both things are interrelated, or we can go with charge density concept also. Okay, we can go with charge density concept also, charge upon size. Okay, so size should be minimum and charge should be maximum for hardness. Okay, you can see this is +6, so charge is maximum as well as size would be minimum, because the complexes or the chromium is in +6 oxidation state. Okay, so it will have maximum charge density, so this chromium would be your hard metal. Is it clear, Tarunesh? This would be your hard metal. Okay, so both factors are considerable, charge as well as size. Yes, everyone. So again, the question is very simple and straightforward. So what is the correct answer for this question? What you have to calculate? You have to calculate the final temperature if initial temperature is given. Okay. So let's solve this question. Okay, what all values have been given? Your Joule Thomson coefficient is given, that is 0.173 Kelvin ATM inverse. Okay, this value is given, and your pressure is given, right? Pressure is given, that is 25 atms. Temperature is given, that is 300 kelvins. Okay, these all values are basically given to you. Okay, so P1 is given and T1 is given. Okay, what we have to calculate? We have to calculate this, that is T2. Okay, we have to calculate T2. Joule-Thomson expansion is carried out from a pressure of 1 atm. So basically, at this pressure, we have been performing this particular right experiment. So what we have to calculate? We have to calculate the final temperature. Okay. So let's solve this question. So what is your Joule-Thomson coefficient? Joule-Thomson coefficient is how we can represent it: the change in temperature by relative change in your pressure at constant enthalpy. Right? This is your Joule-Thomson coefficient. Right? Change in temperature divided by basically change in pressure at constant enthalpy. So this is your Joule-Thomson coefficient. Okay, so now what we can actually do, we have to find out the final temperature. Okay, we have to find out the final temperature. So this is your Joule-Thomson coefficient. Okay, so we can write basically Joule-Thomson coefficient is nothing but change in your temperature divided by change in your pressure. Okay, so we can take this pressure over here, right? dp, we can write dp over here, then we have Joule-Thomson coefficient and dt. Okay, this way we can actually calculate the change in your temperature. Okay, so now this is your small change. Now if I'm including overall change, so this would be delta p mu Joule-Thomson coefficient is equals to delta t. So this is how we can calculate the value of your delta t, right? So now let's solve this question. So what is delta P? Delta P is nothing but P2 minus P1. Okay, this is nothing but P2 minus P1, and this is your Joule-Thomson coefficient. Is this value is nothing but T2 minus T1. Okay, so what is the value of P2? We know the pressure of air, that is going to be your external pressure. Okay, so pressure of air is 25 atm. So this is going to be your P2, 25. Okay, minus the pressure or at which we are just actually performing this experiment. Okay, so the pressure at which we are performing this experiment is 1 atms. Okay, so 25 minus 1 is going to be your del pressure change into Joule-Thomson coefficient. And what is the value of Joule-Thomson coefficient? The value is 0.173. Right, the value is 0.173, 0.173 Kelvin ATM inverse. Okay, this equals to T2 minus T1. We have to find T2 minus T1. Okay, so what is the temperature given? T2 is basically 300 kelvins. The air temperature is given. Okay, so we have to use this value, that is 300. Okay, we have to use this value, that is 300 minus T1. So we can now calculate your temperature value. Okay, so let's do this question, or let's write this way. Let's find out delta T. Okay, let's find out delta T. So all of you just calculate this equation and tell me the value of delta T you are getting. Let's find out delta T, that is change in your temperature. Okay, 25 minus 1, that is 24. ATM and ATM will be cancelled. So 24 into 0.173. Just calculate this, 24 into 0.173. Alright, okay, so you are getting delta T is equals to 4.152 kelvins, okay. So delta T over here is 4.152 kelvins, okay. So now we know what is delta T. Delta T is T2 minus T1 is equals to delta T, okay. This is going to be your temperature T2 minus T1, okay. So what we can say, actually your initial temperature is how much? You have initial temperature 300, so 300 minus 4.152, that is going to be your initial temperature, or we can say final temperature, okay. We can say final temperature, so final temperature would be your 300 minus 4.152. Is it clear to all of you? Any doubts over here? So this value is 300 minus 4.152. So this way we can actually calculate the temperature, okay. So I hope this is clear to all of you. Any doubts? Is it clear, everyone? Any doubts in this question? All right then. So let's take next one now. Yes, Bharti. See, what we are doing, we are using this delta P change. So we use 25 ATMs. Okay, basically, this is basically our P2, or we can take it P1 also. So we did 25 minus 1. Okay, we did 25 minus 1. So corresponding to this pressure, right, the temperature is 300, and corresponding to this your pressure, we have to find out that temperature. Okay, we have to find out that temperature, so we use the corresponding values. Corresponding value of 25 is 300, and corresponding value of 1 is basically your the final temperature, and this difference is equals to 4 Kelvin. Okay, this difference is actually equal to 4 Kelvin. Right, okay, yes, definitely, Path. Delta T is negative when your Joule-Thomson coefficient is positive. That is correct. Okay, so the question says the correct set of information. So complex over here is your MnH2O6. Okay, it's a hexa aqua complex of manganese plus 2, right? And four options says first option is mu observed, that is magnetic movement, experimental magnetic movement is equals to spin only magnetic movement. This is your first option. Observed is greater than spin. Observed is equals to spin. Observed is greater than spin. Okay, then we have second complex cobalt hexa complex in +3 oxidation state. So first option is paramagnetic, diamagnetic and paramagnetic. Okay, so these are four options. So you can use one trick. Okay, of eliminating the options, and you can get to the correct answer. Alright, so let's solve this question. So let's take this complex first, okay? In order to eliminate the options, let's take this complex first. We have cobalt H2O6 3 positive, okay? This is your complex, and cobalt in +3 oxidation state with basically aqua ligands. This ligands is going to be your strong field ligand now, okay? So cobalt oxidation state is your D6, and definitely it's a strong field ligand. So this is how we are going to fill up the electrons: 1 2 3 4 and 5 6. Okay, so what we can observe, that this complex is your diamagnetic complex, not paramagnetic. Okay, so we can cancel out option A and D very easily. Okay, we can cancel out option A and D very easily. Now we have to figure out our answer from option B and option C. Okay, so option B says observed magnetic moment is greater than spin. Option C says observed magnetic moment is equals to spin value. Okay, so the complex is MnH2O6 plus 2, right? It's a D5 complex, high spin. So 1 2 3 4 and 5. Okay, it's a D5 complex, high spin. So for basically your mu observed greater than mu spin, it can only possible, right, in two cases. First is when we are taking LS coupling into consideration, when we are taking LS coupling into consideration, right? And second is and second is when basically we are taking orbital contribution, when we are taking orbital contribution. Okay, when we are taking orbital contribution. So we know that in D5, okay, neither your T2G is unsymmetrically filled nor your EG and T2G is symmetrically filled. So there is no concept of orbital contribution and there is no concept of LS coupling, right? So for D5 system, the mu spin is equals to your mu observed value. Okay, so correct answer would be option B. Option C is going to be your correct answer, not B, option C. Okay, option C is going to be your correct answer. Is it clear to all of you? See, H2O is a strong, it's not, first of all, we cannot define the strength of ligands. Okay, it depends on your type of coordination number the complex is making and your metal. Over here the cobalt is in +3 oxidation state, so with +3 cobalt, H2O is a strong field ligand. Okay, with +3 cobalt, H2O is a strong field ligand. So is this question clear to all of you, that the correct answer would be option C? Any doubts in the explanation? If you have any doubts, just let me know in the comment section. Okay, let's take the next one. If you have any doubts in this question, you can let me know in the comment section. So this is your next question. The coefficient of performance of a Carnot heat pump between high temperature of your 70 °F and a low temperature of 40 °F. So this is your question and you have to calculate the coefficient of performance. Alright then, so let's solve this question. The coefficient of performance of a Carnot heat pump. So basically we have to calculate performance coefficient for heat pump. Okay. Between high temperature of 70 degree Fahrenheit and a low temperature of 40 degree Fahrenheit. So first of all, what point should be clear that we need to substitute the temperature values in Kelvins, not in Fahrenheit. Okay. So we have to convert this Fahrenheit temperature into Kelvins. Okay. So how we can convert this value? How we are going to convert this value? So we have to convert degree Fahrenheit to degree Celsius. Okay, we have to convert degree Fahrenheit to degree Celsius. Okay, so what is the conversion formula? The conversion formula is, let's suppose we have any x Fahrenheit and we have to convert that Fahrenheit to your degree Celsius. Okay, so x Fahrenheit minus 32 into 5 by 9. Okay, x Fahrenheit minus 32 into 5 by 9. So this is how we can convert this formula of degree Fahrenheit to degree Celsius. Okay, so what we need now, we need two temperatures T2 and T1, or we can represent T cold and T hot. Okay, we need two temperatures T1 and T2. T1 is always greater than T2 temperature, so we need two temperatures T cold and T hot temperature. Okay, so let's calculate this first temperature, that is your T hot temperature, 70 degree Fahrenheit. Okay, so 70 minus 32 into 5 by 9, this is your T hot temperature, and T cold temperature is 70 minus 32, 40 minus 32, right? 40 minus 32 into 5 by 9. Okay, this is your T cold temperature. So let's calculate these two values. So T hot would be, what is going to be your T hot value? (21.1). Okay, so 21.1 degree Celsius. Okay, this is going to be your T hot value, 21.1 degree Celsius. Okay, what about T cold then? T cold value would be, it would be approximately, okay, 4.44 degrees Celsius. Okay, so this is your T hot value, this is your T cold value. We'll be adding 273.15, 273.15 to convert this value to Kelvins. Okay, so this value would be now approximately, it will be close to, let's do this calculation. So 0.152. Okay, this would be 4 and this is 9, 294.25 Kelvins. Okay, and this value would be 9, then we have 5, and this is going to be your right, basically 7, right? 7 and 2. So this is going to be your T cold value. Okay, so this is your T hot value and this is your T cold value. Okay, now let's do this calculation. Okay, so what we need, a coefficient, we need coefficient of performance of a Carnot heat pump. Okay, we need a performance of your efficiency performance of your heat pump. Okay, so what is your efficiency performance of your heat pump? Can I write? It's nothing but reciprocal of Carnot engine, right? It's nothing but reciprocal of your Carnot engine. Okay, what is your coefficient of performance of Carnot engine? It's nothing but 1 minus T1 minus T2. Okay, it's nothing but 1 minus T2 minus T1, or we can write down 1 minus T cold by T hot. This is your coefficient of performance of a Carnot engine. Okay, so 1 minus T cold temperature is 277.5, 277.5 divided by 294, 294.25. Okay, 294.25. So this is going to be your coefficient of performance for Carnot engine. Now let's calculate this value. Everyone, just calculate this value and tell me the correct answer of Carnot engine. Okay, so the value is close to 0.05 value. Okay, so now we have to find out for heat pump. Okay, so just reciprocate this value, and the coefficient of performance for heat pump would be 1 by 0.0569, and this value would be now close to, just calculate this value, close to 20. Okay, this value would be close to 20, and you have to report the correct answer basically, right? Not close values. 17.6. Okay, 17.5 or 75, 17.6. So this is going to be your close value. Okay, now the coefficient of performance for heat pump would be 17.6. Is it clear to all of you? Any doubts in this question? Is it clear? Right, I hope this question is clear to all of you. Great. Now let's take next question. Right, okay, so in which of the following coordination intensities the magnitude of your delta O, that is crystal field splitting energy, will be maximum? Okay, so for this question, first step is we have to find out the coordination number. So coordination number is in first complex is 6, coordination number in second is also 6, in third it's also 6, then in fourth it's also 6. Okay, second step is we have to find the metal oxidation state. Okay, so metal is same, that is cobalt, and the oxidation state is also same, that is +3. Okay, now if your metal is same, oxidation is state is same, now the next step is to check the strength of ligands. Okay, so this strength of ligands is basically the last step. First you have to check the coordination number, then the metal and its oxidation state, and last step would be your strength of ligands. Okay, now the deciding factor over here is strength of ligands. So what is the strength of ligands? We have oxalate ion, ammonia ion, then we ammonia basically molecule, then we have water molecule, and we have cyanide ion. Okay, so strength of ligand according to spectrochemical series. Okay, so this is going to be your strength of ligands. Is it clear to all of you? This is going to be a strength of ligands. Okay, so cyanide is basically strong field ligand over here. So what we can say that the basically this energy gap for option D would be maximum. Okay, energy gap for option D would be maximum. Is it clear to all of you? I hope this question is clear. Okay, this is your next question. uh right, basically an aqueous solution of nickel 2 plus. Okay, an aqueous solution of nickel 2 plus, which is your A, on reaction with ammonia gives B, and B on reaction with ethylene diamine gives C. Okay, so there is a complex, that is your aqueous complex of nickel, right, that is your A, and when we are reacting A complex with ammonia it gives B, and when we are reacting B with ethylene diamine, it gives C. Okay, so what we have to find out, the color of octahedral complexes. The color of octahedral complexes. So these are four options given. Okay, so Tanu is going with A, Tarunesh A, Astha A, Aruna C. Alright, what about others? We have 8 people live in this session, okay? Alright then, let's start solving this question. So the question says an aqua complex of nickel, okay, and all these complexes are octahedral complexes. They have mentioned this point also, okay. So nickel in +2 with aqua ligand, okay, so 6 plus 2. Then this is your A complex, okay. So now it is being reacted with your ammonia and it gives you B complex, okay. So NH3 6 plus 2, this is B complex. Then it is reacted with ethylene diamine, it gives 3 complex, okay. So this is your C complex, right? This is your C complex, okay. So we have these 3 complexes A, B and C, okay. So now what we are going to do, right, the first thing is a coordination number, okay. We have to go step by step. So coordination number is 6, 6 and 6, okay. Second step is a metal and oxidation state, Ni plus 2, Ni plus 2, Ni plus 2, okay. So coordination number is same, metal in oxidation state is also same, okay. So now next thing over here is the strength of ligands, okay. So this is your H2O, this is ammonia and this is ethylene diamine, okay. So what is the strength of ligand? Can I write this is your spectrochemical series? First we have ethylene diamine, then we have ammonia, then we have H2O. So this is your strength of ligands. Okay, ethylene diamine, then we have ammonia, and then we have H2O. Okay, so now if this is your strength of ligand, so what can I say? That energy gap in third complex, okay, or in C complex is greater than energy gap in B complex, and this value is greater than your energy gap in A complex. Okay, this is your energy order. Okay, is it understandable, everyone? Okay, this point is clear how I have just wrote this energy order. Is it clear to all of you? Energy of C complex is greater than energy of B complex, and energy of B complex is greater than energy of A complex. Clear? Okay, so let's go to next point now. Now if this is your energy order, so definitely, right, if this is your energy order, so it will absorb lambda of less wavelength. C complex will absorb lambda of less wavelength. Okay, so lambda of C is less than lambda of B and is less than lambda of A. Okay, lambda of A. So this is your lambda value. Okay, this is your lambda energy value. Lambda of C is less than lambda of B is less than lambda of A. Okay, now we got this thing that lambda of C complex is less than lambda of B and is less than lambda of A. Okay, so now if it absorbing wavelength of less wavelength, right, if it's basically absorbing light of less wavelength, so it will reflect light of more wavelength. Is it clear? It's complementary color theory. If it absorbing light of less wavelength, so this will emit light of your more wavelength. Okay, so if I talk this emission, okay, if I talk emission, so C complex will emit light of high wavelength. Okay, then B complex, then A complex. It will absorb light of less wavelength, but it will emit or it will reflect light of more wavelength. Okay, so let's go with complementary color theory. This is our color wheel diagram. So we have 6 sections over here. Okay, we have 6 sections over here. Vib Okay, we have 6 sections over here. Vibgyor. Okay, so this is your Vibgyor. So basically what will happen, it will reflect or it will emit light of more wavelength. C complex will emit light of more wavelength. Okay, so now if I just see these options, okay, so first is blue, green, violet and violet. Okay, blue, green, violet and violet. So which is the light of more wavelength? If I write down Vibgyor, okay, if I write down a Vibgyor, we have blue, green and violet. We have these 3 colors, blue, green and violet. Okay, now if I want to arrange them in your wavelength value, so wavelength, according to wavelength, green has maximum wavelength. Okay, then we have blue, then we have violet. Okay, green has maximum wavelength, then we have blue, then we have violet. Okay, so definitely this is your maximum wavelength, so this color corresponds to your C complex. Is it clear? This color corresponds to your C complex. Okay, so now if we have green value over here, so this will corresponds to your C complex. Okay, so basically your C complex, that is your ABC. Okay, this green color corresponds to your C complex. Okay, then after this particular complex, what we have? Okay, then we have basically B complex. Okay, then we have C, B and then D. Okay, so this is your color order. So this will actually absorb, right, this C complex will absorb energy of your less wavelength, and it will emit energy of your more wavelength. Okay, so according to this concept, what should be your correct answer then? Right, okay. So green color is of maximum wavelength. That means this color is of maximum wavelength. So absorption is of minimum wavelength. Minimum wavelength absorption means, right, maximum energy. Okay, this way we can relate this thing. Green color is of basically high wavelength, so it will absorb low wavelength and it will emit high wavelength. Okay, so if it is basically absorbing low wavelength, so that means basically it is basically a strong field ligand, okay, of high energy. So we have green over here because ethylene diamine is basically your strong field ligand. Okay, so we have green, then we have blue, and then we have violet. Okay, so correct answer over here is option D. Is it clear to all of you, everyone? Any doubts in this question now? If you have any doubts, right, please feel free to ask in the comment section. Correct answer over here is option D. Okay, because green is of your maximum wavelength. So if I compare this thing, this absorption is of basically, right, this is option is your minimum wavelength. Okay, and minimum wavelength corresponds to your high energy. Is it clear? All right, great. Now let's go to next question now. Right, okay. See, in these type of questions, when we have so many complexes to answer, okay, we have to take help of options. So what we are going to do, we are going to pick one common example, okay, that we have been, that basically we are practicing from so long now, okay. So we know we can figure out this complex and we can figure out this one also. This is coordination number 4, and if it's coordination number 4, so definitely it's a square planar complex, and square planar complexes are generally diamagnetic. Okay, or what we can do, we can start off with this complex also. This is nickel plus 2. This is nickel plus 2, and in plus 2 oxidation state, water is your weak field ligand. Okay, so we have D8 electronic configuration, 1 2 3 4 5 6 7 8. Okay, we can see that we have two unpaired electrons, so this is your paramagnetic complex. Okay, so fourth is your paramagnetic complex, and we have to figure out diamagnetic complex. So we have fourth in first option, so we can cancel out A option. We have fourth in D option, we can cancel out D option also. Okay, so we have actually cancelled out two options. Now next thing is, I'm going to see these two options, 2 3 5 and 6, 1 3 5 and 6. So 3 5 and 6, this thing, okay, 3 5 and 6, these three complexes are common in option B and option C also. So I'm not going to check these three complexes to save my time. Okay, so 3 5 and 6 are present in both the options, so I won't see these two options. Okay, so now we have to check complex 1 or complex 2. This is our complex 1 and this is our complex 2. Okay, we can check any of these complex. So let's start with this complex. Okay, this is iron plus 3. Okay, iron plus 3 D5, and iron plus 3 D5, and cyanide is a strong field ligand. Okay, so how we can fill up these electrons? 1 2 3 4 5. Okay, we know we have one unpaired electron, so it's going to be your paramagnetic complex. Okay, it's not diamagnetic, it's paramagnetic. So I can cancel out option B also. Right, I can cancel out option B also. So correct answer would be option C. Okay, so hardly it will take 30 seconds for you to solve this question. Okay, and most of the students will definitely get trapped in this question. They will start solving each and every option. You don't have to do that, you just have to see the options and try to eliminate as many complexes as possible. Okay, so this is the correct way of solving this question. Correct answer would be option C. Okay, I hope it's clear to all of you. Let's go to the next one. Sure. Okay, the question is, a graph is plotted between this value. Okay, now what is this value? E minus E naught cell by RT. So this is your y-axis versus log Q. Q is your reaction quotient. Okay, log Q is basically your x-axis, and E minus E naught by RT is your y-axis. Okay, so this is your graph. So where N1, N2 and N3, these three values, N1, N2 and N3, represents number of electrons involved in that particular chemical reaction. Okay, what you have to find? You have to find the relation of these three N values. Okay, so which of the following is correct? N2 greater than N1 greater than N3, first option. N3, N2, N1, second option. N1 is equals to N2 is equals to N3, and fourth option is N1 greater than N2 greater than N3. So these are three options. So what you can do, I think you are present in Telegram channel, okay? So what you can do, you can actually go to Telegram channel. So there is a message pinned over here, and right on that particular message, just click on that message. So and join the WhatsApp group, okay? So there's a WhatsApp group also. You can join that group. I'll share the PDFs over there. All right, so let's solve this question. So what is the question saying? The question is a graph is plotted, all right, for these type of reaction. So what we can write, E is equals to E naught cell, okay, E is equals to E naught cell minus RT by NF log Q. Q is your reaction question, the basically amount of your product divided by reactant. Okay, so this is your reaction. E minus E naught by RT is your y axis. So E minus E naught by R, right, is equals to E minus E naught minus RT by NF log Q. Okay, log Q. So E minus E naught by RT is your y axis. So I'm going to take this RT over here. So this would be now, okay, this would be minus 1 by F log Q. Okay, this would be minus 1 by F log Q. So now this is your part. So what we have to write down? We have to write down E minus E naught RT versus log Q. So now this, if this is your y axis, so what we can write, that E minus E naught by RT is your y axis, right, minus of 1 by n. Okay, this represents your number of electrons. So what we can write, that 1 by NF is nothing but your slope. Can I say this thing, 1 by NF is nothing but your slope, right? I hope you can relate with this expression. 1 by NF is nothing but your slope. Okay, this is how we can find this value, and it's in a log, so we can write 2.303 also. Okay, it's in log, so we can write 2.303 also. Okay, now the slope is basically this value, minus 2.303 by NF. Okay, we have to find relation in number of electrons. Now see, if this is going to be your slope, let's write down slope is minus 2.303 NF. Let's ignore this 2.303 and F value, which is basically your constant value. Okay, so anyhow always this will give you some constant value. So I can write slope is nothing but 1 by n. This is going to be a variable value, 1 by n. 2.303 and F is going to be your constant value. Okay, so now if I increase, see, just try to relate this graph. Okay, if I increase value of n, see, just think like this, if I'm increasing value of n or number of electrons, what will happen? Slope will decrease. Yes or no? Is it clear? If I am increasing n value, slope will decrease because it's in reciprocal plus negative value. So if I am increasing the right n value, slope will decrease. Okay. So let's go to this graph now. So for which value of n slope has maximum value? So for which n slope has maximum value, n1, n2 or n3? So for which right n value slope has maximum deviation, or we can say we have maximum slope? For n1, right? For n1 slope has maximum value. Okay, you can see what is your slope. You can take tangent of that value, you can take tangent of this right slope or this curve, or you can find out the difference. So for yellow line, see, for yellow ink, this is going to be your slope. So this will give you max more value. Okay, so the tangent is basically high, the theta is high. What is your slope? Slope is nothing but right, y2 minus y1, x2 minus x1, or we can write dy by dx, or we can write slope is equals to tan theta. So if theta is increasing, it means slope will also increase. So over here your theta is increasing. Okay, over here the theta is basically decreasing. So now what we can write down? We can write in this way. If I want to write down the values, so slope is maximum for n1, then for n2, then for n3. So slope is maximum for n1, n2 and n3. Okay, so now if slope is maximum for these values, so number of electrons, okay, so basically n1, n2, then n3. Okay, so slope is maximum, so this is going to be your value. So let's write down slope. Okay, not number of electrons, let's write down slope. Okay, so slope of first graph, or basically slope of n1, is greater than slope of n2 is greater than slope of n3. If this is the case, so what we can write down? Yes, everyone. So what is the correct relation then? If this is your slope, that means number of electrons is decreasing. Okay, number of electrons is basically decreasing. So can I write number of electrons of n3 is greater than n2 greater than n1? Just take 30 seconds and try to just digest this information. If slope of 1 is right maximum, so what it means? N is slope is maximum. If slope is maximum, n would be minimum. Okay, number of electrons would be minimum. If for n1 slope is maximum, so number of n1 electrons would be minimum. So what would be the number of electron relation then? N3 greater than n2 greater than n1. Is it clear to all of you? Any doubts? See, just take 10 seconds and try to just understand all this information. Okay, I'm giving you 10 seconds. Slide is right there in front of your screen. Just understand this relation and write down in the comment section if you have any doubts. Is it clear to all of you? Can I expect that this information is clear? It's clear for to all of you. So correct answer would be option C then, n3 greater than n2 greater than n1. Right? Is it clear, Bharti, Rajendra, Atanu, Aruna? Is it clear, Vaibhav? Okay, we have Astha, Sachin. I hope it's clear to all of you. Great. Okay, so let's go to next one now. Alright, okay. So what we have to find out the correct order of wavelength of absorption in the visible region, okay. Correct order of wavelength, okay. So we have to find the correct order of wavelength of absorption. See, just you have to pick all these points of absorption, not of emission. Of absorption, okay. So you don't have to use complementary color theory over here. You're getting my point? So these two things are very important, okay. You don't have to use complementary color theory over here because they are asking for absorption, not for emission, okay. So they are asking for absorption, so you don't have to use complementary color theory, okay. So the correct order for the wavelength of absorption in the visible region, okay. So for that we need to write down the correct order for strength of ligands. We need to write down the correct order for strength of ligands, right? So we have nitride, we have ammonia and water. So this is your correct order. Is it clear? This is your correct order. NO2 minus NH3 H2O is your correct order of strength, okay. Now first step is always checking out the coordination number. Coordination number is 6, 6 and 6, right? And oxidation state is +2, +2 and +2, nickel over here. So coordination number is 6, oxidation state is +2. So we have to go with strength of ligands, okay. So this is your strength of ligands. So energy would be in this order only. NO2 minus NH3 and H2O, okay. And see, you are correct, Atanu, right? This basically nitride over here is your nitrogen donor. So it's a basically nitrogen can donate from oxygen as well as, right? Nitrogen can basically, this nitride is an ambidentate ligand, okay. It can donate with your oxygen as well as nitrogen, okay. When they have represented this ligand in NO2, okay, it's not visible, right? Just give me a second, I'll explain it again. Okay, I hope yellow ink is visible, right? So now let's discuss this question. Right, so what we have to find out, see, the strength of ligands, okay. So we were talking for this NO2 minus, okay. So nitride is basically oxygen donor, right? It can donate from oxygen as well as from nitrogen, okay. So when they have represented in this format, you have to take nitrogen donor, okay. When they have represented in this format, then you have to take oxygen donor. So over here they are using nitrogen donor, okay. Just check spectrochemical series once. This NO2 is a strong free ligand if I compare ammonia and NO2, okay. So this is your strength of ligands. So what can I write? See, let's suppose this is your A complex, okay, this is your B complex and this is your C complex, okay. So if I want to write down the correct energy order, so definitely A would be greater than B would be greater than C. So this is the correct energy order for energy, right? Next is we have to find the correct order for wavelength. So wavelength of A would be least, then B, then C. So correct answer would be, yes everyone, correct answer would be option A. Is it clear to all of you? Any doubts? Correct answer would be option A. Right? Very good, Parth, Rajendra. Correct answer, Aruna. Correct answer would be option A. Any doubts to anyone? Is it clear? Okay, so here's the next question. So let me read it. What we have to find out, according to the Nernst equation, the potential of an electrode changes by 59.2. It's not 39.2, it's 59.2. It's 59.2. Okay. So the question is, according to Nernst equation, the potential of an electrode changes 59.2 millivolts whenever the ratio of the oxidized and the reduced species changes by a factor of 8, 10. Okay, so basically whenever it changes by the factor of 10, the potential of electrode changes by 59.2. What would be the corresponding change in the electrode potential if the experiment is carried out at 30 degrees Celsius? So this thing you have to calculate, okay? So when we are carrying out this experiment at 25 degrees Celsius, the relation of electrode potential change and your concentration is given. So you have to find out what would be the ratio change, what would be the change in electrode potential if we are carrying out this experiment at 30 degrees Celsius. So this is your question. All right, so let's start solving this question. So first of all, we have to make this habit, okay? whatever is given, we have to write those things in physical chemistry. In this way, a question would be very simpler and we can approach the question with less distractions. Okay, so according to the Nernst equation, the potential of an electrode changes by 59.2 millivolts. This is your delta E value whenever the ratio of oxidized and the reduced species changes by a factor of 10. Okay, so ratio of oxidized and reduced is given 10. Okay, at 25 degrees Celsius. So what would be the change in electrode potential if the experiment is carried out at 30 degrees Celsius? Okay, so this is the information given and we have to calculate at 30 degrees Celsius. So now we know, okay, what is your equation for E naught cell. So for equation of E naught cell is E is equals to E naught cell minus RT by NF. Okay, or if we are using in log, so let's go with log equation only. So this would be 2.303 RT by NF log. Okay, and let's suppose we are writing in this format. Let's take, this is basically x1. E1 is equals to E naught cell minus 2.303 RT NF log x1. Okay, so after this step, E2 is basically nothing but E naught cell. Okay, when we have changed the concentrations, it would be 2.303 RT by NF log x2. Okay, so when we have changed the concentration, this value would be changed and E1 and E2 would be changed because E is basically concentration dependent, not E naught. Okay, so temperature would be constant, number of electrons involved would be constant, 2.3 R and F, they all are constant values. Okay, so we have now two equations, 1 and 2. Okay, we have two equations, 1 and 2. So now what I'm going to write down, we know that this delta E is given to us. Okay, so delta E, what I'm going to do, I'm going to subtract 1 minus 2. So delta E, E1 minus E2, basically this value is equals to E cell and E cell would be cancelled out. So this value would be equal to 2.303 RT by NF. Okay, 2.303 RT by NF log into this factor, and we know this factor is given to us, that is 10. Is it clear to all of you? This step is clear. Any doubts in this step? Is it clear? So this is your step. Okay, so this value is given and we know log 10 is basically 1. Okay, so 59.2 millivolts is equals to 2.303 RT by NF. So we got this value actually. Okay, we got this value, we got this relation that 59.2 millivolts is nothing but 2.303 RT by NF. Right? Okay, now next thing is, we know if we perform this experiment at 10 degrees Celsius, at 25 degrees Celsius, this value is 59.2 millivolts. Okay, what we can actually do, see, we can find out the value for 2.303 R NF, which is a constant thing. Okay, we know this value is constant, this is constant, this is constant, and this is constant. Only temperature is variable over here. Okay, so 59.2 millivolts is equals to basically 2.303 R divided by NF into temperature. Okay, we can write this way. So we can find this value. So this would be 59.2 divided by temperature is nothing but 2.303 by RNF. Okay, 2.303 by RNF. So this way we can calculate this value. Okay, we can actually calculate this value. Now what I'm going to do, see, this value is now calculated. So let's take a fresh slide. So this is now 59.2 divided by temperature is equals to 2.303 R by NF. So we got this expression. Okay, now what I'm going to do, I'm going to find out this value. Okay, so this is nothing but your delta E. This value is nothing but your delta E, right? So now I'm just going to substitute the values. So this would be now 59.2, right, into the temperature is 30. 30 plus 273 is your 30 plus 273 is your 303. Okay, 30 plus 273 is basically your 303. Okay, so we got now 303 kelvins. So divide into 303 divided by 298, that is your 25 degrees Celsius. So we just have to calculate this value. So now this value would be 60.2 millivolts. Is it clear to all of you? Any doubts over here? So this is how we can calculate this value. So this value would be now 60.2 millivolts. Okay, we got this expression. So what we actually did, we substituted this value. Okay, we got this expression, we just substituted this value with 59.2 T, and this is basically your E. Okay, so this part is clear to all of you. Any doubts? Any doubts how we calculated the final answer? Okay, right. So let me explain this part again. So this part is clear. This part is clear to you, Aruna. 59.2 is equals to 2.303 RT by NF. This is clear how we got this expression. Clear? Okay. So see, let's do one thing. Let's erase this one also. Okay, let's do one thing. Let's erase this part also. So we got this expression. Okay, we got delta E is equals to 2.303 RT by NF. Okay, you can see this was the expression. Delta E is equals to 2.303 RT by NF. Okay, so we got this value. So case 1 is, let's write down case 1. So case 1 is when your temperature is 25 degrees Celsius, the change is 59.2. So 59.2, 2.303 R, temperature is 25, so 298 Kelvins divided by NF. When temperature is 298, the change is 59.2. Okay, so from this part we calculated this value. 59.2 divided by 298 is nothing but 2.303 R by NF. So this is clear. We calculated this value because this is your constant in two equations. Okay, so 2.303 R by NF is nothing but 59.2 by 298. Okay, so this is our third equation. Okay, so now what is your case fourth? Case fourth is basically when we have to calculate at 30 degrees Celsius. Okay, so again delta E is nothing but 2.303 RT by NF. So we have to find this value, that is delta E. So 2.303 R by NF is nothing but 59.2298. Okay, we just calculated this value is nothing but 59.2 by 298. Okay, so we got this value. Now see this part I'm taking. Okay, this equation I'm taking, delta E is 2.303 RT by NF. So we have to find this value at 30 degrees Celsius. So we got this value which is equals to 59.2298. Okay, now I'm going to substitute this temperature value which is 273 plus your temperature value, that is 30 degrees Celsius. So that is your 303 Kelvins. Okay, this is your Kelvin, this is in millivolts. So this and this will be cancelled out. So you can find out the value at 30 degrees Celsius, which is close to 60.1 millivolts. Now you got the answer. Now you got the expression how we actually calculated this value. Is it clear to all of you? Any doubts? Okay, I hope it's clear. Now let's go to next problem. Let's see if we have more questions also. So we did this problem, this one also. Right, we did this one. This is also completed. This one also. This is also completed. Okay then. Right. Okay, so we have three more problems. It's better to complete it now only so that we can take more questions in upcoming class. So this is your next question. Right, okay. The question is very simple. Nickel with chloride. We know nickel with chloride. It is now, it is basically in tetrahedral geometry, okay. Nickel with square planar. Only cyanide is responsible for square planar complexes in, right, Ni2 plus complexes. So correct answer is option B. Okay, nickel with aqua is your hexa aqua complex, right? So correct answer is option B. Very good, all of you. Let's go to the next one now. So the question says, consider the following statements for 18 aniline. The correct statement is or are. So it could be your MCQ also or MSQ, right? So you have to decide that. First statement is it is aromatic. Second statement is the inner protons resonate at delta 9.28 at 1H NMR. C statement is there are 6 protons in the shielded region. D statement is there are 8 protons in the d-shielded region. See, take some time and try to analyze the question, okay? Don't be in hurry. In examination, you will have enough time if you approach the question in the right direction. So don't just be focused towards answering the question. Be focused how you have to improve, how you can improve your accuracy, okay. It matters the most, okay. See, if you are able to do only 70% of your examination, right, so then the accuracy matters, okay. If you are giving answers in a correct format, in a correct way, so definitely you're going to score much higher than the students who are just trying to attempt 90% of the examination, okay. So just focus on your accuracy and have some patience. Read the question carefully and just then give your answers, okay. So it's not about how fast you are giving the answers, it's about how fast you can give answers with accuracy, okay. So how fast you can give correct answers, okay. This part matters the most, right. Rest is, I hope you can take this advice, okay. I hope you can take this advice because it's very important, okay. Accuracy is the most important thing in examination, okay. Yes, time management is also important, but accuracy is more important because anyhow this won't give you right marks if you're attempting 100% examination and you are not correct, okay, you are not accurate. So accuracy plus time management, this will save your examination, okay. So let's go with the statement now. So consider the following statements for 18 aniline system. So 18 aniline is like this, okay. We have discussed one part on 18 aniline in yesterday's session also. So this is your 18 aniline system. Right, this is your 18 aniline. Okay, so how many carbons we have? We have 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 and 18. Okay, so we got 18 carbons now. Now we have to just draw the pi electrons. So we have pi electrons over here. Let's suppose over here, so it would be here, right? Okay, so this is your 18 aniline system. So definitely it's aromatic. 4n plus 2 is equals to 18. So this is aromatic. So A statement is correct. The inner protons resonate at 9.28. If it's aromatic, so definitely inner protons would be shielded protons. It will give you value in negative chemical shift. Okay, this is incorrect statement. There are 6 protons in the shielded region. Let's find out. 1, okay, 2, 3, 4, 5 and 6. Definitely we have 6 protons in shielded region. We have 6 protons in shielded region. Option C is also correct. Okay, there are 8 protons in de-shielded region. Let's find out how many protons we have in de-shielded region. So we have 1, 2, 3, 4, 5, 6, 7, 8, right? 9, 10, 11 and basically 12. So we got 12 protons in de-shielded region and 6 protons in shielded region. Okay, we did this question in yesterday's lecture also. So we discussed this part over there, right? There are 12 protons in de-shielded region and 6 protons in shielded region. So correct answer would be A and C. Is it clear to all of you? I hope it's clear. Let's go to the next one now. Yes, people. So, what is your answer for this question? Only 2 of you answered, and we have 9 people live on this basically class. So, the question is consider following statements for binding energy per nucleon versus mass number curve. Okay. So, let's discuss this question now. See how we can relate binding energy with your right? Binding energy per nucleon with your mass number. Okay. So, we can draw this curve. We know this is your curve. This is the nature of curve for binding energy. Binding energy, right? This is basically binding energy per nucleon, and over here we have atomic number. Okay, binding energy per nucleon, and over here we have atomic number. Okay, so the graph looks like this. Okay, the graph is like steep increase, then after this maximum point it goes to some constant decrease. Okay, it is decreasing, but the change is not steep, the change is not high. Okay, this is your graph for binding energy. Okay, now let's understand each and everything related to this curve. Okay, first of all, what we are discussing binding energy per nucleon. Okay, per nucleon, how much binding energy is there, so how much energy is required to take that electron out. Okay, in that, from that particular nucleus. Okay, basically in nucleus we have protons as well as neutrons. Okay, so how much binding energy is basically exerted by this nucleus on electrons. Okay, so what we can say that binding energy per nucleon is directly proportional to stability of nuclei. Can I say this thing? Binding energy per nucleon is directly proportional to stability of nuclei, right? I hope we can relate binding energy per nucleon with stability of nuclei. Okay, first point. Second point is, let's understand this curve. Okay, so in this curve basically we have two regions. Okay, we have two regions. This is region 1 and this is region 2. Okay, so we got two regions, region 1 and region 2. So which region corresponds to fission and fusion? So which region is for fusion and which region is basically for fission? Anyone? Which region is for fission and which region is for fusion? Yes, okay. First for basically fusion and second for fission. Okay, how we can understand this concept? See, this region, okay, this region will have particles, or this region will have atoms for low atomic number. Okay, less atomic number. So if they are of small size, so definitely they have possibility to bind with each other. Okay, if they are of small size, so they can actually bind with each other and they can result in a big molecule. So this process is known as fusion. Okay, fusion, that means these two molecules are combining with each other. Okay, so this is your fusion. Fission means degradation of molecule. Okay, basically we have a big molecule and it goes to two small molecule, and that happens only when the atomic mass is basically high. Okay, the stability is less or the atomic mass is high. Okay, so this is termed as your fusion and fission. Okay, so example for fusion is your hydrogen bomb, right? Hydrogen bomb. An example for fission is basically your nuclear bomb. I hope you can relate with this point. Right, the example for fission fusion is hydrogen bomb. Hydrogen is a small molecule, right? An example for fission is your nuclear bomb. So these are atomic molecules, just like we have uranium. Okay, for uranium we can prepare atomic bonds, we can prepare nuclear bombs. So that is an example of fission. Okay, and the first one, the region 1, is an example of hydrogen bomb. Okay, now if I want to compare the energy released, okay, from fission and fusion, so what can I say if I compare the energy released from fission and fusion? So energy of fusion, right, is greater than energy of fission. That means if right, we have hydrogen bomb, so energy released by hydrogen bomb would be greater than energy released by fission. So these are some points for this particular curve. Now what is this maxima point? Okay, now what is this maxima point? So this maximum point tells you about the maximum binding energy per nucleon. Okay, which is approximately close to 8.6 to 8.7. Okay, this value is approximately close to 8.6 to 8.7, all right, electron volts. Okay, basically mega electron volts. So this is your energy value. Okay, and this value corresponds to your iron atom. This value corresponds to your iron metal. So what we can say, that iron is the most stable nuclei. Iron is having the most stable nuclei. Okay, so this value is approximately 8.6 to 8.7 for iron. Okay, so this is for iron. And what is the atomic number for iron? 56. Okay, iron atomic number is 56 and the energy is 8.6 to 8.7. Okay, so now with this information we can solve this previous question. Okay, so the question was what we have to find out the correct statements. Okay, it is maximum for iron, definitely it's maximum for iron somewhere around 8.6 to 8.7 mega electron volts. Okay, next is its average value is about a 5 megavolts. No, its average value is about 8 point something. Okay, you can see the average value is not 5. Okay, this is not your average value because most of the particles are over here, right, in region 2, so average value is not 5. Okay, so definitely option B is incorrect. It is almost constant for most of the nuclei. Yes, okay, after this steep curve, right, it is almost constant for this region. Okay, and most of the nuclei falls under this region. Okay, so correct answer is option C also. Okay, it is almost constant for most of the nuclei. Next is it increases rapidly for low mass nuclei and then becomes almost constant. Yes, definitely it increases rapidly for low nuclear, right, low mass nuclei, then it becomes constant for high mass nuclei. Okay, so correct answer is A, C and D. Is it clear to all of you? Any doubts over here? Any doubts in the question? So those of you who are new in this session, right, in the description box you'll find the Telegram channel. You can join that particular Telegram channel for notifications about upcoming classes, YouTube sessions, and the plus courses. Okay, and if you are a 2022 aspirant or if you want to prepare for upcoming master level entrance examinations, you can use this referral code SBATRA for plus subscription. Okay, you can use this referral code for 10% discount on your plus subscription. So I hope you found this session useful. ये topic uh, definitely, right, see you can understand this topic also, right, you can understand this topic. This is from your nuclear energy part. Okay, binding energy is from your nuclear energy part. So if you have covered nuclear energy part, then definitely this is your topic. Okay, from jam point of view. But if you haven't covered it nuclear energy, so you can leave this part. Okay, so it's not fixed that question is going to come from this part. Okay, it's having 50% probability. So if you have covered nuclear chemistry, you can go read about this topic. If you haven't covered, you can skip this topic. Okay, so you don't have to pay a lot of attention to this topic. Okay, anyhow, I hope you found this chapter useful, these questions useful. If you have any feedbacks to give, you can let me know in the comment section. Okay, I'll see you in the next class and I'll share the PDF also. Take care everyone. Bye, have a good day.